Our third method of being able to solve systems of linear equations is solving by elimination. Some books call this solving by addition or subtraction. Our textbook calls it solving by linear combinations. But most of the books that I've used and most of my students know it as solving by elimination. Our other algebraic method, solving by substitution, also involved eliminating a variable. So the process is going to be somewhat similar. We're trying to create a situation where instead of x's and y's, we have just x's or just y's, so that we can solve for just that variable and then substitute that back into our original equation, either one of them actually, to find out the other coordinate for our ordered pair. So first, when we take a look at this system, 2x minus 3y equals 6, 4x minus y equals 8. For most of my students throughout the time that I've been doing this, they feel like elimination is the easiest method. It's the one they understand the most. But there's also a huge hurdle to overcome. A lot of my students want to automatically just add the equations up. They want to do this, 2x and 4x, and say that's 6x, 3y, negative 3y minus y, and say that's minus 4y, and then equals 14. And then go from there. They want to start moving things around in the equation. The thing is, this doesn't get us anywhere closer to being able to solve this equation than we were when we started, when we had two equations. We can't just randomly add these together. We need opposite coefficients on one of the variables, so that when we add them together, the coefficient will be 0, and that variable term will drop away. So if we look at our equations, 2x minus 3y equals 6, 4x minus y equals 8. I can see that 4 is a multiple of 2. If I multiply the first equation by negative 2, negative 2 times 2 will be negative 4. I'll have negative 4x and positive 4x. When I add those two together, my x coefficient will be 0, and that term will drop away. So let's make that happen. Negative 2 times 2x, negative 4x. Negative 2 times negative 3y, positive 6y. Negative 2 times 6, negative 12. Our second equation can stay as is. 4x minus y equals 8. Now I can add them together. Negative 4x, positive 4x. Sums to 0. 6y minus 1y is 5y. Negative 12 plus 8 is negative 4. And on to solve that equation, y equals negative 4/5. Remember that our solution to a system of linear equations is going to be an ordered pair. So let's take y equals negative 4/5 and write it inside a set of parentheses. So we're writing this as an ordered pair. Next, I need to find out what's the x-coordinate of the solution. I know the y-coordinate is at negative 4/5. What's the x value that makes y equals negative 4/5? I can go back to either one of my original equations, whichever one seems easiest to use, and substitute our value in. So 4x minus negative 4/5 equals 8. 4x plus 4/5 equals 8. From here we can approach this in any way that we want. It might be easiest to go ahead and take the fraction out. So let's multiply by 5. 20x plus 4 equals 40. Simplifying this down, both divide by 5. 36 divided by 5 is 9. 20 divided by 5 is 4. I'm sorry, both divided by 4. 20 divided by 4 will give us 5. So our x value is 9/5. Our y value, negative 4/5. Let's look at another example. In this case, I see that I don't have one coefficient, the multiple of another, as far as integer multiples. Negative 5 and 7, negative 12 and 8. I don't have a number that I can multiply times 8 that gives me 12. What do we do here? Well, if I can multiply one equation through, as long as I multiply on both sides, I can multiply both equations through. I can multiply 5 and 7 say, and eliminate the x variable. I could also look at my negative 12 and my 8. Recognize that they have a common multiple, a least common multiple of 24. 2 times 12 is 24. 3 times 8 is 24. And this kind of keeps my numbers a little bit smaller. Most of my students find these easier to work with. So let's make that happen now. 2 times 7x, 14x. 2 times negative 12y, negative 24y. 2 times negative 22 will be negative 44. Similarly, bottom row, 3 times negative 5, negative 15x. 3 times 8y, 24y. 3 times 14, 42. Let's add them up. 14 minus 15, negative 1. The y's sum to 0. We did that on purpose. That's why we multiply by 3 and 2, so make that happen. Negative 44 and 42, negative 2. So x equals positive 2. I'm going to write that into my ordered pair. Let's go and substitute that back in and find a y value now. Negative 5x plus 8y equals 14. Well, my x is 2, so negative 5 times 2 plus 8y equals 14. Let's add 10 to both sides. (24) divided by 8 is going to give me 3. So my solution is the ordered pair 2, 3. One more example. It's very possible for a system to have no solution or infinitely many solutions, all real numbers. Let's look at an example of what that looks like when we try to solve algebraically. So as a for instance, negative 4x plus 8y equals negative 12. 2x minus 4y equals 7. I see the negative 4 and 2 have a relationship. I can multiply my second equation by 2. So 2 times 2x, that's 4x. 2 times negative 4y, negative 8y. 2 times 7, that's 14. Negative 4x plus 8y equals negative 12. Add them up. 4x minus 4x goes to 0. 8y minus 8y goes to 0. The entire left side of the equation equals 0. On the right side, negative 12, positive 14, 0 equals 2. Well, that's a false statement. 0 will never equal 2. What that tells me is there's no value of variables x and y I can substitute in that will make this a true statement. So because of that, this system has no solution. Finally, let's go ahead and take a look at what does this look like if we use elimination to solve a word problem. So a jar with quarters and dimes in it. Very common kind of word problem that involves solving a system of linear equations. A total of 47 coins worth $7.70. We're asked to write and solve a system of linear equations to determine how many quarters are in the jar and how many dimes are in the jar. Well, we know from previous days we're going to have a pattern. We're going to have one equation that is the number of things. Another equation that's going to involve money. Almost all the time, this is the way things are going to play out. What's our important information here? Well, there's two types of coins. There's quarters and there's dimes. Short sleeve t-shirt, long sleeve t-shirt. Small pizza, large pizza. Half sandwich, full sandwich. Adult tickets, kids tickets. Whatever the variety of question, whatever information we're talking about, it boils down to the same set of relationships. So two types of items, quarters and dimes, for a total of 47 coins. I also know that a dime is 10 cents, quarter is 25 cents, then I have a total of $7.70. So let's go ahead and lay things down. My number of things, I have quarters and I have dimes. If I add those two together, they're the only two kind of coins that I have, it's going to equal my total number of coins, which is 47. So Q plus D, or X plus Y, whichever variables you'd like to use, that's one equation, equals 47. My number of dollars. Every quarter is 25 cents. How much money do I have in quarters in this jar? I don't know. However many quarters there are, times 0.25. How much money do I have in dimes? Well, 0.1 times D, however many dimes I have, is going to give me that value, and then times 770. All right. We know that we can clear out these decimals by multiplying this equation times 100. 25Q plus 10D equals 770. Let's multiply this equation times negative 10. Negative 10Q minus 10D equals negative 470. So now I've got two equations. One variable has opposite coefficients. I can add. 25Q minus 10Q gives me 15Q. 10D minus 10D, that term drops away. 770 minus 470 equals 300. Divide both sides by 15. Q is my number of quarters. There are 20 of them. Okay, how many dimes? Well, I know quarters plus dimes equals 47. So Q plus D equals 47. My Q is 20. Substitute that in. We subtract 20 from both sides and find out that D equals 27. So our answer, we're asked the question in words, we'll give our answer in words. 20 quarters, 27 dimes. So that's our practice problems for solving systems of linear equations by elimination.